Hi there! In our last two videos we covered a lot of information about substitution ciphers. Today in this video I want to round off the discussion by introducing a field of study known as cryptanalysis. If cryptology is the process of encrypting and decrypting a secret message with a known key, then cryptanalysis would be the process of deciphering an encoded message without the key. In other words, cryptanalysis is the art of breaking the code. Since cryptanalysis is a rather large topic, I'll only be talking about two cryptanalysis methods today, the brute force method and frequency analysis. So with that, let's begin. Now before we talk about how to attack a substitution cipher, let's quickly remind ourselves what some of those ciphers are. Now this list is not exhaustive, but these are some of the more common substitution ciphers that you will run into. If you do need a refresher for these ciphers, then you can always go back to the first two videos in this series, but for now, let's talk about how to break these ciphers. In the world of cryptanalysis, there are many types of attacks that we can use, but as I mentioned, I'll only be focusing on the brute force method and frequency analysis for this video. So let's start by taking a closer look at the brute force method. Now this is by far the easiest method to understand, and in most cases the easiest to implement, but as we'll shortly see, it's also the most likely to lose its effectiveness the more complicated a cipher becomes. We perform a brute force attack when we begin examining all possible combinations to the problem from beginning to end. We start with the first possibility and we keep going on and on until we come up with a solution, assuming that the solution falls within one of these possibilities. Now as an example, let's take a look at the Caesar cipher and see what it would take to brute force the code and find a solution. As you may recall, the Caesar cipher generates a key by shifting the alphabet a certain number of letters to the right. The number of letters we shift by, in this case represented by the letter X, is modded by the length of the alphabet, represented by the letter M, and in return we get a number which represents our key. To decrypt a message, the receiver would have to have foreknowledge of this number, which he could use to create his own substitution alphabet. But what if we don't know how many letters the alphabet was shifted by? How do we decipher an encrypted piece of text when using the Caesar shift when we don't have the key? By now the answer may be obvious. With the Caesar cipher, an attacker can brute force his way to an answer by starting with a substitution alphabet using x equals 1, attempting to decrypt the message with the key, and continuing to shift by 1 until the secret message makes sense. As you can see, breaking the Caesar cipher doesn't require a lot of effort. And in truth, the main reason it was effective back in the days of the Roman Empire was because most people really couldn't read at the time. But this begs the question, since this worked so well for the Caesar cipher, does this mean that the brute force method is always so effective? Well, as I mentioned earlier, it depends on what cipher we're looking at. Let's take a look at some of those other ciphers and see how susceptible they are to the brute force method. Let's start with the @bash cipher. We learned in a previous video that the @bash cipher generates its key by taking the alphabet and reversing it. This means we only have one way of generating the key. If an attacker wanted to decode a secret message without knowing the key, the only thing he would need to know is that the message was encrypted using the @bash cipher. After that, it wouldn't be difficult for the attacker to figure out the rest, and the code could be broken on the first try. With the ROT13 cipher, we have the same situation, only this time with a different type of key. In the ROT13 case, we generate our key by splitting the alphabet in half and substituting each letter occurrence in the secret message with its paired letter. Once again, there is only one way of generating this key, which means an attacker only needs to know that this was a ROT13 cipher in order to decode the message. And what about the Caesar cipher? We've already looked at this one, but let's count the number of possibilities required to figure out a proper key. Now assuming we stick with the English alphabet, there are only 25 possible ways of generating a key. An attacker might take a little bit longer to break this code than the @bash or the ROT13 ciphers, but it's also unlikely his coffee would go cold before he figured out the answer. So that leaves us with the last cipher in our list, the deranged alphabet, and this is where things start to get interesting. The deranged or mixed alphabet cipher builds its key by taking letters of the alphabet and placing them in random locations. Each letter can only be used once, and we can also take the optional step of scanning the alphabet for any matching letter pairs. So, how many possible keys can this cipher generate? We can figure out the math by looking at the number of possible locations left after each letter is placed in the substitution alphabet. In the beginning, there are 26 possible locations for the first letter to be placed. For the next letter, we now have 25 possible locations since one of those positions have now been occupied. The next letter has 24 possible locations, followed by 23, 22, 21, and so on until we arrive with only one spot left to take the last letter. If we multiply these values together, we can see that this is the same as figuring out the factorial for the number of letters in the alphabet. When solved, we come up with this massively large number of 4.03 times 10 to the power of 26. And when written out, it gives you a number that you see here. This is the number of possible keys we can come up with for the deranged alphabet. Also, as a quick aside, I just want to mention that in the computer world, we might also be interested in knowing what this number would look like as a base 2 format, or in other words, its binary equivalent. Figuring this out gives us approximately 2 raised to the power of 88, which can also be referred to as an 88-bit encryption key. Whichever way we decide to write it, the question is, what does this mean for our brute force attack? Well, to put this number into context, imagine if a person decrypting the message were to try each possible permutation of the mixed alphabet, making one guess every second. Let's also assume the worst case scenario where they don't find an answer until the very last guess. How long would it take him to figure out the answer? To be able to go through all the possible keys, the math says we would need slightly less than 13 quintillion years to complete this task. By comparison, the age of the entire universe from the Big Bang to present day is approximately 13.8 billion years old. Now that's a lot of guesses. Even with the super fast processing power of computers, you can see that the brute force method is not very effective here. So great, you might think we found the perfect cipher. If it takes someone that long to go through all of the possibilities, then this is obviously the best method to encrypt our messages. Except it isn't. It's not even close. The problem is that all substitution ciphers are susceptible to a different kind of attack known as a frequency analysis, and that's what we're going to look at next. So to start, the term frequency analysis is just a fancy way of saying letter counting. These letters can appear either individually by themselves, or we can look for patterns to emerge within small groups of letters. Frequency analysis has been around with us for a long time, dating back to around the year 800 AD, although there is some evidence to suggest that it could have been around much earlier than that. Now with any language, it's possible to analyze large samples of text and count the number of times each letter appears in that text. Eventually, we should have enough information to demonstrate a pattern of distribution for each letter based on its frequency of use. If we stick with the English language, it should surprise no one to know that the letter E comes out on top as the most commonly used letter in the English alphabet, with an approximate 13%. This is followed by the letters T, A, and O making out the top 4. And if we look at the least used letters, we see the letters J, X, Q, and Z rounding the bottom 4. Altogether, the pattern of letter frequency looks a little something like this, starting with the most frequent letters all the way down to the least frequent. Now keep in mind, as I mentioned before, this is only for the English language. If we were to look at another language like French, for example, we would see a different letter pattern. And if we look at a language like Spanish, an even different pattern appears. If you're curious about letter frequency distributions for each language, you should take some time and head over to the letterfrequency.org site and check out their letter frequency tables. Of course, when doing frequency analysis, we don't have to restrict ourselves to single letters. We can also look for small groups of letter patterns. In this case, we refer to single letters as monograms, groups of 2 letters as bigrams, we have trigrams for groups of 3 letters, and finally quadgrams for groups of 4. We can continue adding letters if we want, but for most cases, we start to see a significant drop in effectiveness after 4 letters. I should also mention that when I refer to a group of letters, I don't mean to imply that only groups of letters that form complete words should be counted. While you can have groups of letters that form words like at or the or that, this isn't always necessary for frequency analysis to work. The quadgram TION, for example, is a frequent letter pattern we see in the English language. This letter pattern appears in words like station or action, even though the letter pattern isn't a word by itself. Now, it is possible to write an application that can use these letter patterns to analyze an encoded piece of text, and we'll talk about that part in a bit. But the truth is, most of us already know this stuff through intuition when we're taught language. In fact, it's so simple that most of us can decode complex substitution ciphers using nothing more than a pencil and paper. Cryptograms are a good example that use the pencil and paper approach. As you may already know, cryptograms are puzzle games that contain messages encoded using the deranged alphabet cipher. The letters in the messages can be paired up with other letters, numbers, or even graphical symbols in some cases. In this example, the numbers 1 to 26 are used to represent a specific letter in the alphabet, and it's up to you to figure out which number is paired with which letter. Now note that not every letter appears in the puzzle, so not every letter in the key will have a matching number. As we saw previously, we already know that certain letters appear more often than others, so we can leverage this by seeking out numbers in the puzzle that appear more frequently. The number 8, for example, appears several times throughout the puzzle, so we can assume it represents a letter with a high frequency. There are also 2 3-letter words that happen to have the same letter sequence, and this provides us with another clue that we can use to figure out this puzzle. And since the puzzle maker has given us the second letter in each word, and because they both start with a letter paired with the number 8, this is a good place to start as any, so we'll start looking here for a solution. Now, if we stick with a strict definition of the letter frequency, we might start solving this by trying out letter combinations from the top 5 letters, E, T, A, O, and I. However, I can't think of too many 3-letter words that start with a constant followed by an R. A better choice might be to look at the 5 vowels ordered from most frequent to least frequent. So we start off with the letter E and try to think of any 3-letter words that begin with ER. Honestly, no words really come to my mind off the top of my head, so let's try moving on to the next letter. So what about the letter A? At this point, I can already think of several 3-letter words that start with AR. Words like art, arm, arc, R, and so on. It's important to note that I'm not even thinking about the substitution key at this point. I'm just using my intuition of language to make some educated guesses. By understanding language, I eliminate the need to go through each letter permutation and instead focus on the letter combinations I know will work. So moving on, since the word R, A-R-E, is a very common word, let's try substituting the last letter with an E. To figure out if this is correct, we can start looking at other parts of the puzzle, such as the next word over. If we try substituting in our letters, it should be obvious we've formed the word really, R-E-A-L-L-Y. So great, our guess was a good one. The next step is to update the encryption key with our findings and then fill out the other numbers in the message with their corresponding letters. This process continues like this until we finally solve the puzzle. And as you can see, even though I mentioned a while back it would take around 13 quintillion years if we were to guess each possible encryption key, we've already managed to solve this puzzle in minutes thanks to our ability to identify words and letter patterns. Now there is another example where we see this type of frequency analysis happening all the time. I'm of course talking about that famous game show Wheel of Fortune. Now the biggest difference here is that contestants aren't given a substitution key, but instead they try to uncover a secret message by guessing each letter on the board. The more letters they guess, the better the chance they have of solving the puzzle. Fans of the show might also be familiar with the famous letter sequence R-S-T-L-N-E, which happens when the last contestant standing plays in the final round. In the classic version of the game dating back in the 90s and early 2000s, the show would let contestants pick 5 consonants and 1 vowel before solving the puzzle. Almost always, contestants would choose the letters R, S, T, L, and E, most of them likely not even knowing why they were picking those letters. The only thing they knew is that everyone else was picking them, so they probably should too. And if you think about it, it makes sense. Those 6 letters are some of the most common letters in the English language, and choosing them greatly increases your chance of solving the puzzle. In fact, the letter sequence became so common that in modern day Wheel of Fortune, they now just give the contestants the R, S, T, L, N, E, and ask them to choose an additional 3 consonants and 1 more vowel. And by the way, if you do end up on the show and you want to use your knowledge of letter frequency to help you get a better chance of winning, might I suggest choosing the letters H, D, C, and A. Tell Vanna I said hi. So with that, we've covered the by-hand approach to breaking substitution ciphers. What if we wanted to write a program to do the work for us instead? With computers, we need a slightly different approach than the one we've been using so far. The problem here is that humans come built in with an innate understanding of language. We learn it when we're a child, and by the time we're in grade school, we already have a good understanding of what a word is. Computers, on the other hand, don't come built in with that same understanding for language. This means we'll first need to teach them how to recognize words before we can ask them to decide if a message looks something like language. So how do we go about doing this? Well, to solve substitution ciphers with a computer, there are generally 4 main steps required to build our program. The first step is to build a table containing a list of possible letter patterns along with how likely they are to appear within a language. The more likely the pattern, the closer we are to finding legitimate words. Once we've built our table, we can then start to decode our secret messages. We do this by making an initial guess with a random key and then attempting to decode the message with that key. We analyze the decoded text and give it a score. The score is determined by the frequency of the letter patterns within the text using our text pattern table from step 1. The next step is to alter the key slightly and try again. For example, we could shift 2 random letter locations or even generate a new key entirely. We make another attempt to decode the message and again give it a score. If the score is the highest score so far, we keep track of the key that gave us that score. If the score is lower, we return to the key with the highest score, shuffle it around again, and make another attempt. This can continue on for thousands of iterations with new keys being generated until the program ends. Afterwards, we should hopefully have a key that gives us a good decryption of the encoded message. It may not always work on the first try, but eventually we should be able to find a good fit. So let's first look at how we can build a table of letter patterns and figure out their frequency. The best way to go about this is to simply find a very large piece of text, format it, and record the number of times each letter pattern appears within the text. We can then use these numbers to figure out their probabilities, which will help us analyze the secret message later on. Now, the source of the text we use for the analysis doesn't really matter, just so long as it's very large, with lots of word combinations. But the book War and Peace by Leo Tolstoy, for example, contains a little less than 590,000 words, making this a very good place to look. Now, to further refine this example, I've grabbed the opening paragraph, but the process I'm about to show you should be done across the entire book. The first thing we do is convert all letters into the same case just to make things a little easier for us, and then we remove all spaces, punctuation, and numbers until we have a single string of text. We then look at each letter sequence in the text, building up our bigrams, trigrams, and quadgrams, but we'll stick with 4-letter quadgrams for now. Whenever we arrive at a new letter pattern, we add it to a table and set its count to 1. We then shift over by 1 letter and look at the next sequence of letters, again adding it to the table if it's not there, or incrementing its counter if it's already been added. This goes on until we've arrived at the end of the text and we now have our table of letter patterns. Now, using this method, I did write up a quick program to build a list of quadgrams from a copy of the book War and Peace I found on the Project Gutenberg website, and these are the results I came up with. In total, I was able to count almost 62,000 unique quadgrams in the text I used. However, others might have different results depending on what text they're looking at. If we look at the top 10 quadgrams in the table, there are some very common letter groupings you might recognize, including the letters THE appearing in a variety of different patterns. And if we look at the bottom 10, we can see some rather unfamiliar letter groupings that only appear once in the entire book. It should also be noted that even with a very large set of text, it's not possible to have every letter combination make the list. Later on, we'll see how this can cause us a bit of a problem and how we can overcome that problem, but for now, let's move on. So as of right now, we have a table that has a count of each quadgram, but this only helps us to understand the number of times each quadgram appears in a book. What we need to know is the likelihood each quadgram pattern can be found in the English language. For that, we'll need to take our number counts and turn them into a probability. And probability is just the ratio of the number of occurrences divided by a total number. For example, if we take the first quadgram from the list, THAT, we can find its probability by dividing the number of times it appears in the text, in this case 8,284, and divide it by the total number of quadgrams in the table, in this case 61,828. And this gives us an approximate 13% probability that the quadgram THAT will appear in any given piece of text written in the English language. And as we saw with the letter E, 13% is a pretty decent number. And we do this for all other entries in the table, and the application can now understand which groups of letters are more likely to appear in the English language and which ones are less likely. So how does this work? Let's take a look at a scrambled sequence of letters as an example, and we'll see. To anyone who can read English, it should be obvious that this is not exactly a kind of word pattern that we might find in the English language. But to a computer, it's just a sequence of letters. To help the application determine how likely this letter sequence belongs to English, we'll need to figure out the probability of this letter sequence. So keeping in mind that we're focusing on quadgrams for now, we have to first break down the letters into individual quadgrams and then multiply the probability for each quadgram together. When multiplied together, this gives us a probability of around 3.5 times 10 to the minus 5% for the entire letter sequence. Now keep in mind that even though this number is very small, its meaning has no significance unless we compare it to other letter sequences of the same length. In a sense, the number we've come up with can be thought of as a score for this letter sequence, and we must score other letter sequences to determine which sequence wins. So let's try this again with a different letter sequence. Now this time we'll use a letter sequence that we know forms a word. We'll do the same steps as before. We'll first extract the quadgrams from the letter sequence, and we'll use the lookup table to determine their probabilities before multiplying them together. This time the letter sequence comes out to a score of around 1.0 times 10 to the minus 4%. And now we can compare the scores for each letter sequence side by side. The important thing to note here is that one letter sequence has a higher score than the other letter sequence, This doesn't mean that the application knows for certain that the letter sequence strike is an English word. It's just that the sequence is more likely to appear in the English language because it has a higher score. The hope here is that the closer we get to English, the higher the score when we compare to other sequences that don't match English. We'll see an example of this in action when we conclude the video. For now, let's briefly switch gears, and I'd like to talk a little bit about two problems that have come up. One of them is what to do with really small numbers, and the other is what to do when a letter sequence doesn't appear in the table. Let's start by talking about what to do with the really small numbers. We can see from this slide that the numbers that we have calculated have both come out to very small numbers. This is the result of multiplying several numbers together, and this only happened when we used a sequence of 5 letters. If we were to start multiplying probabilities for even larger pieces of text, the numbers would come out to even smaller than this, leading us to a problem in software development known as a floating point underflow problem. Just as computers have a problem holding really large numbers, they also have a problem holding really small numbers. So to solve this, we can actually do a little trick here using logarithms. We simply take each probability in the lookup table and then determine their base 10 logs. We now have numbers that are a little more computer friendly, as we'll see in a moment. If we go back to our example again, this time we'll use these log values to figure out the score for each letter sequence instead of their probabilities. And once again, we need to break down the letter sequence into its quadgrams, but this time we'll take the log of the product for each quadgram probability multiplied together. And just to remind everyone, one of the rules from the laws of logarithms states that if you multiply values inside a log function, you get the same result as you would if you were to add the log values for each item individually. And this is what we do here. We add together the log values for the probability of each quadgram, and since we're now dealing with the addition of numbers rather than their multiplication, we can come up with numbers that are a lot more manageable for a computer. Again, this number is just a score, and it has no real meaning until we compare it with other letter sequences of the same length, so let's do that now. We once again take the word strike and add together the logs for the probability of each quadgram and come up with a score. And when we compare the scores for each word, we see that the letters strike are still more likely to be English than its counterpart because it has a higher score. So this means we've now solved our first problem. The second problem I mentioned is what do we do with letter sequences that don't appear in the lookup table. As I mentioned before, even with extremely large pieces of text, it's not always possible to have an entry for each letter sequence imaginable. This time the solution is very simple. We simply create a floor value that can be assigned to each letter sequence that doesn't appear in the table. And the method I prefer to use is to take the smallest value from the last entry in the lookup table and simply multiply it by 2. Now whenever an unfamiliar sequence appears in our secret message, we can assume the likelihood of it being in the English language is very low, and we can give it this floored value. So let's finish everything off by going through a quick example of an application that can help us decode a secret message. We'll start off with our secret message, and then we'll try to use what we've learned so far to decode it without knowing what the key is. Assuming we've already built up our frequency table, the next step is to generate a random key and use that key against the secret message. We then run our frequency analysis against the attempt, looking for bigrams, trigrams, and quadgrams, and then we come up with a score for the attempt. We always want to track which key has the highest score, and since this was our first attempt, we'll add this key to a box called Best Match. Next, we'll generate a new key by swapping around a few letters at random. We'll make another attempt to decode the message, and then we'll score it. Since this attempt has a lower score than our first attempt, we'll skip it and move on to the next attempt. And so this continues on for thousands and thousands of iterations, generating new keys and scoring the attempt. At some point, we should be able to determine the correct key, and when we score it, it should have a much higher score than all other attempts. Of course, even with the perfect match, our program still doesn't know for sure that this is the correct key, so it continues on making new keys. But at some point, after say 1,000 iterations after the last time we updated the best match box, the program realizes it won't get a better match than its current best match, so it gives up. By the end, we should hopefully have the correct key and the decoded secret message. But you may need to run the program a few times before it finds what you're looking for. And there you go, that's it. This concludes my 3-part series on substitution ciphers. In the first part, we looked at what a substitution cipher is, and in the second part, we looked at how to create a program that encodes and decodes secret messages using substitution ciphers. And finally, in this video, we looked at what it would take to crack an encrypted message using brute force and frequency analysis. I hope you found these videos helpful, and I thank you for watching them. I look forward to seeing you again sometime in the future, so thank you for watching.